Hi everyone, time for some probability here. So we'll finish this section on continuous random variables and move on to something else next week. But the first thing I wanted to start with today is this business of taking a normal random variable with mean, mu, and sigma and converting it to a so-called z-score, okay? Which we said had the standard normal distribution, namely it has mean 0 and standard deviation 1. Okay, so first of all, let me just say, let me share this with you. Let me just say that it is critically important that you understand what it is that Z is actually telling you, okay? So that's why I want to spend some time on this at the very beginning. So let's do that. Okay, so first of all, Z, okay, Z, well, here, let me just say on the front end, X, we're assuming has the normal distribution with mean mu and standard deviation sigma, okay? And we said, okay, Z, we're setting equal to X minus mu over sigma, okay? And it makes sense that Z would have the exact same distribution, because after all, when we take X and we subtract mu, all that's doing is just shifting everything by mu units in one direction. So like the whole distribution would look the same. And then dividing by sigma, well, all that's going to do is just take the whole distribution and kind of scale it by sigma. So it's not going to change the shape of the distribution at all. It's going to look the same, and therefore it makes sense that this would be normal. So let's just say that this is normal also. All we've done is subtracted a number and then scaled it by a constant, right? Okay, because look, Z is equal to X minus mu over sigma, but you could also think of that as just like 1 over sigma times X minus mu. Okay, 1 over sigma times X minus mu. So basically we've taken X, shifted it by its mean, and we've scaled it by 1 over sigma. And so if you think about what that's going to do to the distribution or the density, it's going to have the same kind of shape, okay? So what is the mean of Z? Okay, what is the expected value of Z? Okay, we claimed that it's 0, okay? And it is, because look, I can actually factor out 1 over sigma. After all, that's a constant, yeah? So this is going to be the expected value of X minus mu, okay? But of course, once we do that, okay, again, we were doing the expected value of Z. We had this is 1 over sigma times the expected value of X minus mu. And this is equal to 1 over sigma. Okay, and look, you can just use the linearity of expectation. This is the expected value of X minus, what's the expected value of mu? Well, that's just mu, right? That's just mu. Seriously, okay? But this right here is also mu. So this is 0, right? So the expected value of this new random variable that we've created, the z-score, is 0, okay? And secondly, I would remind you that if we take the variance of some number times a random variable plus some other number, we've talked about this before, but the plus b part, that doesn't do anything, okay? The plus b part doesn't do anything, but remember, multiplying the random variable y by a, and the reason I'm using y is because I've already used up x, okay? And I'm just wanting to remind you of this formula. What happens with a, though? Well, that actually scales the variance by the square of A. So this is like A squared times the variance of the original random variable Y, okay? So you will recall that formula. So what about the variance of Z? Okay, what about the variance of Z? Okay. All right, the variance of Z, okay? Well, once again, this is the variance of what? Of 1 over sigma times x minus mu, okay? And of course, this is just the variance of 1 over sigma times x minus mu over sigma, okay? Minus mu over sigma. And now I can kind of see, look, this part right here is kind of like the plus b, right? This guy right here is kind of playing the role of a, and then this part right here is kind of like the b. Does that make sense? So this is like ax plus b, where b incorporates that minus sign, okay? So this is going to be, I would have to just factor out the a. The b part doesn't do anything. If I factor out the a, this is going to be 1 over sigma squared. 1 over sigma squared times the variance of x. But the variance of x, for crying out loud, that was also sigma squared. And so we get 1. Okay, so the variance of z is 1, which, by the way, means that the standard deviation of z is also 1. Okay, so z is distributed as normal with mean 0 and standard deviation 1. If z is related to x by the formula x minus mu over sigma, okay? So another thing I wanted to point out was the following. I mean, look, this stuff is just critically important to understand what's coming down the pike here. So that's why I'm spending some time on this. Again, z is equal to x minus the mean divided by sigma. That's the same thing. Like if I multiply through by sigma, that means that sigma z is equal to x minus mu, which means, by the way, that x, the relationship between x and z, is that x is equal to mu plus z times sigma, okay? So what does that mean? Well, so z equal 1, so for instance, if z is 1, that means that x is equal to mu plus sigma. So what does that mean? If x is equal to mu plus sigma, that means that x is 1 standard deviation above the mean, okay? Okay, I'm putting a little plus right here to remind us that this is plus 1. So this means that x is 1 standard deviation above the mean, above the mean. And let me circle this plus again to kind of remind you of that. So what if, okay, so let's go to another page here. I know that x is equal to mu plus z times sigma. Okay, what if z was like -1? Okay, and again, there's a minus sign here this time. So what would happen if z was equal to -1? Well, then x would be equal to mu plus -1 sigma, which, by the way, is mu minus sigma. Okay, so here what would be true? If z is -1, that means that x is, look at what this says. X is 1 standard deviation below the mean. And how do I know below? Or how would I know below? Well, because look, there's a minus sign right there. So all this to say, okay, so let me just kind of bring this little discussion home here. All this to say that the formula x equal to mu plus z sigma, shows that Z measures the number of standard deviations above or below, above if it's positive, or below if it's negative, that shows that Z measures the number of standard deviations above or below the mean. Sorry, I meant to say the mean here, okay? The mean mu that X is. Okay, so if X is one standard deviation above the mean, Z will be 1. If X is 2 standard deviations above the mean, Z will be 2. If X is 1.5 standard deviations above the mean, Z will be 1.5. If X is 3.7 standard deviations below the mean, if X is 3.7 standard deviations below the mean, Z will be negative 3.7. Okay, that's just something that's worthwhile to keep in mind, that there's that this is a critical, right? This is important. Okay, this is important right here. Knowing the relationship between X and Z and being able to interpret that correctly and keep that within our cognition is an important skill to have, to be sure. Okay, another thing that I wanted to point out is the following. Okay. All right. So suppose, okay. So so again, X is distributed as normal, mean mu, and standard deviation sigma. Okay. Z is equal to equals X minus mu over sigma, and that's going to be distributed as normal with mean 0 and standard deviation 1. Okay, you can kind of draw a little picture of the distribution for X, the distribution function for X over here. And it's going to be a little bell-shaped curve like this, right in the middle. Oh man, that's a horrible picture. Let me erase this real quick. Okay, so here is the distribution for X. Okay, so here is the mean right here. Okay, and I kind of mentioned before that the inflection point, right through the inflection point, that's 1 standard deviation to the left, and right through the inflection point over here is 1 standard deviation to the left, right? So 1 standard deviation to the left, 1 standard deviation to the right. Okay. If I go over, okay, so over here we're talking about X, right? So this is the distribution for X. But for Z, right, I can kind of translate everything over into Z land. Okay, it looks the same. The shape of the graph is the same. It's still normal. But now right in the middle we have 0. And 1 standard deviation to the right is 1. And 1 standard deviation to the left is -1. Okay, so that is, you know, there's this correspondence here between that and that, right? 0 like corresponds to the mean, right? A z score of 0 corresponds to the mean of X itself. Okay, a z score of -1 corresponds to 1 standard deviation below. Okay, so that's kind of the picture I have. And of course you could go to 2 standard deviations or 3 or whatever you want to do, or even like, you know, some decimal number of standard deviations above or below. Okay, and you would have this picture. But the other thing I wanted to point out is that there is a consistent percentage of data. And by the way, doing this allows us to just concentrate on the standard normal to compute various percentages. Okay, this gives us the freedom to do that. I don't have to deal with like you know, infinitely many normal distributions for various means and standard deviations. I can always just convert over to the standard one and deal with that instead. But there's another thing I wanted to point out, and that is the following. Okay, So if I have, okay, so let's just deal with the standard normal here. Okay, if I have the standard normal, okay, 0 is right in the middle. Okay, here's 1, here's -1. So that's 1 standard deviation above, 1 standard deviation below. How much area do you think there is uh, is in this 1 standard deviation bandwidth between 1 and -1? So what do you think the probability, so I mean, here, let me ask it this way. What is the probability, because of this symmetry, I really only need to know like what's going on between 0 and 1. If I can figure out what's going on between 0 and 1, I will know the area between -1 and 0 also. Okay, so like what's the probability that 0 is less than z is less than 1? Okay, what is that? What does that equal to? Okay. Well, you already know, for instance, that okay, let me actually go over here and we'll go into Excel. Okay, so I want the probability that z is between 0 and 1. Okay, so let's do that. Probability that z is between 0 and 1. Okay, so I'm going to do that here. Let me blow this up a little bit. Okay, so I want the probability that 0 is less than z is less than 1. Again, we don't concern ourselves with equality. That's not that big of a deal. Okay, so what is this equal to? Well, it's going to be equal to normal standard distribution. A normal standard distribution, what's the z I'm interested in? 1. And I do want the cumulative. Okay, minus, and now I just want the probability below 0, but we actually know what that is. We could plug it in to the cumulative distribution function and get it that way, but I don't have to do that. I can actually just say, well, I know that that's 50%. Okay, and I get 0.34. Does that make sense? I get 0.341 whatever. Okay, and so watch this. That means the probability that z is within 1 standard deviation of the mean, right? The probability that actually any normal random variable is within 1 standard deviation of the mean, because after all, we can go back and forth from any normal random variable to the z distribution through the formula x minus mu over sigma. Okay, remember z is literally keeping track of the number of standard deviations above or below. So this is the probability that we are within 1 standard deviation of the mean. That's what this is. How would I get this? Well, it would just be twice this. This is going to be 2 times this thing. Okay, right, 0.683, right? Basically, 68% or something. So 68% of the data is within 1 standard deviation of the mean if we're dealing with a normal bell-shaped curve. Okay, what about this? Okay, what about the probability that 0 is less than z is less than 2? Okay, so that means I'm above the mean 0 and at most 2 standard deviations above the mean. What's that going to be? Well, equals normal standard distribution. Okay, 2 comma, okay, cumulative, yes. And of course, I still want to subtract 0.5. I get that. Okay, so what does that mean? The probability that -2 is less than z is less than 2 is going to be? Well, it's going to be 2 times this. Okay, so about 95%. About 95%. That's fairly amazing. Okay, 95%, 95.5% really, is basically is basically the percentage of data that happens to be within 2 standard deviations of the mean, within 2 standard deviations of the mean. And then let's go out to 3 and just see what happens. The probability that 0 is less than z is less than 3. What's that? Well, that's going to be normal standard distribution, 3, 1. Okay. Oops, sorry, I forgot to subtract. Yeah, I need to subtract minus, right? I need to get rid of 0.5. Okay, so 0.4985. So what's the probability that -3 is less than z is less than 3? That means I'm within 3 standard deviations of the mean. Well, that's going to be 2 times this thing right here. Okay, and you get 99.7% of the data. 99.7% of the data. Okay. Also, I mean, it's kind of nice to actually have the the probabilities. I mean, let me just kind of write them down here. What about the probability that one is less than z is less than 2? Okay. So that would be the probability that z is more than 1 standard deviation and less than 2 standard deviations away from the mean. Well, that's got to be the difference between these two things right here when you think about it. Okay. It's got to be the difference between those two things, but let's just go ahead and use the cumulative distribution function to find it. So it'll be normal standard distribution 2, cumulative yes, minus normal standard distribution 1, 1. Okay. And I get that. And just to check ourselves, so this would be equal to, it should be equal to this guy minus this guy, and it is. Yeah, just to make sure we're on the right page. And then let's actually compute the probability that 2 is less than z is less than 3. Okay. Well, that's going to be equal to, what will that be? It should just be this guy minus that guy. Yeah, should be this thing, and then I take away the stuff between 0 and 2. And I'll go ahead and do that. So equals this minus that. Okay. And it's kind of nice to have these little probabilities on hand. It's nice to have these little probabilities on hand because I can fill in this picture that I was dealing with over there. Okay. So I am going to copy these down over in this picture I was starting to draw on the iPad. So let me go over there. Okay, let's see. I'll stop sharing this. Okay, and we'll go over here and I'll share the screen and we'll start filling this thing in here. Okay, here we go. So what did we discover? Well, we discovered that this probability was 0.3413. Okay, and that's this stuff right here, 0.3413. And of course, if that's 0.3413, then this is also 0.3413. Okay, and then what about if we went out to 2 and down to like -2? Okay, well, you know, between 1 and 2, what we discovered was that it was like 0.1359. Between 1 and 2 is 0.1359. Okay, and that's what this would be as well, 0.1359. Okay, and then finally, if I were to, you know, kind of extend this out and go out to 3 over here and down to -3 down here, look at this picture, beautiful. Okay, it's a beautiful picture of what's happening with the normal distribution in general. Okay. What did we discover? Well, between 2 and 3, I got 0.0214. Okay, so 0.0214. Okay, and over here it was 0.0214 also. 0.0214. And what about this stuff? You know, what about that percentage right there? Well, that's 0.6426, right? So, or 0.6426 basically, or 0.6826 actually, 0.6826. So basically that means that to be within one standard deviation of the mean, there's about a 68% chance, a little bit over 68% chance of that happening. Okay. And what about between or within two standard deviations of the mean? Of course, we could add this together, but what is it? So let me just, I'm gonna kind of go like that and write the percentage right there. We ended up getting 0.9545. 0.9545. Okay, so that means about 95.5% of the data is within two standard deviations of the mean. And then finally, what about all the way out to 3 standard deviations? What do we get? Well, in that computation that we did in Excel, we got 0.9973, 99.7%. 0.9973, right? 9.9973. So 68% of the data in a normal bell-shaped curve is within one standard deviation of the mean. A little bit over 95, like 95.5% within 2 standard deviations of the mean. 99.7% of the data is within 3 standard deviations of the mean. 3 standard deviations of the mean. Okay, so that's fascinating stuff there. That is exciting. So we have a good feel for how this stuff is working. Okay, so let's go do a couple of problems here. Okay, stop sharing that. Okay, we'll go over here and we'll put this thing up, and we'll try sharing this instead. Okay, what do we have? So yeah, we know everything we could ever want to know about this. Okay, so let's put this to full screen mode and we'll start messing with this. Okay, here's a problem. The maximum speed of a certain type of moped has a normal distribution with mean 46.8 kilometers per hour and standard deviation 1.75 kilometers per hour. Consider randomly selecting a single such moped. So again, we have 46.8 kilometers per hour. Okay, so we have a mean of 46.8 kilometers per hour, and we have a standard deviation of 1.75 standard deviations per hour. So the mean, I'm writing this down so we can use it, is 46.8. The standard deviation is 1.75. And we're selecting a random such moped. What is the probability that the maximum speed is at least 48 kilometers per hour? Okay. And what is the probability that maximum speed differs from the mean value by at most 1.5 standard deviations? Okay. The maximum speed differs from the mean value by at most 1.5 standard deviations. Okay, so let's let's check this out. Okay, so let me share the screen here. Start this thing, and we'll get going. Okay. Okay, here's our beautiful picture that we just came up with. Okay, so the setup for this problem is the following. Okay, so we had a normally distributed random variable. Okay, the mean was 46. The mean was 46.8. Okay, I'm not really sure why this thing isn't updating just yet. There we go. Yeah. Okay, and what is the standard deviation? So it's sigma equal to 1.75. Okay, they wanted to know that they wanted to know the probability that the speed is at least. Okay, so hang on a second here. Okay, so let me see. Sorry, guys. Just checking to make sure I have the problem down right. So the maximum speeds have mean 46.8 and standard deviation, the other thing. Okay, we're randomly selecting what's the probability that the maximum speed is at least 48. At least 48. Okay, so at least 48. So we want the probability that x is greater than 48. Okay, now there's a couple of ways that we could do that. We could either actually use Excel straight up with this mean and standard deviation, or we could actually convert things to a z-score. Okay, so this would be equal to the probability that I could actually just say, you know, x minus mu over sigma is greater than 48 minus mu over sigma. Okay, I can convert both these things to their respective z-scores. Okay, so this would be the probability that z, because x minus mu over sigma is z, is greater than, okay, what's 48 minus 46.8? Well, that's like 1.2. 1.2 divided by 1.75. Okay, so I could compute it using either one of these. All right, either one of these would be perfectly acceptable. So what I'm going to do is go and actually go into Excel, and we'll take a peek at that. So here we go. Okay. All right. So what is the deal? Okay, so we wanted the probability that x was greater than 48. Okay, what is that? Well, I could just use the normal distribution flat out. Okay, it's saying what is x? Okay, well, hang on a second. If I want to use this, I need to go 1 minus this, right? 1 minus the normal distribution, because it's got to be 1 minus the probability that x is less than 48. So it's normal distribution, x 48. What's the mean? Well, it's 46.8. What's the standard deviation? As for the standard deviation, 1.75. Okay, and I want it to be cumulative. And I get that. And basically the way that I did this, just to kind of be clear, this is equal to 1 minus the probability that x is less than 48. I don't concern myself with being equal. These are all continuous distributions. So that's how we computed that particular thing. The other thing that we could have done is we could have said, well, this corresponds to the probability that z is greater than, I had 1.2 divided by 1.75, okay? Which, by the way, is equal to 1 minus the probability that z is less than 1.2, 1.2 divided by 1.75, okay? All right, let's see. So let's have a peek at that. So that's equal to 1 minus the probability, right? This, what am I saying? So it's going to be the normal standard distribution, okay? And I would put in the corresponding z value I'm concerned with. This time, I mean, you can actually let Excel, you know, do the math for you. And I want this thing to be cumulative. Boom. And of course, they are exactly the same, just as they should be. Okay, so let's go back into our presentation. There we go. Okay, let x have a normal distribution. Oh, sorry. We weren't quite done yet. What is the probability that maximum speed differs from the mean value by at most 1.5 standard deviations? What is the probability that maximum speed differs from the mean value by at most 1.5 standard deviations? Well, that means that I'm no more than 1.5 standard deviations above or 1.5 standard deviations below. Okay, so what do I really want here? Well, in this case, I actually want the probability. So let's kind of think about this together. I don't want to be more than 1.5 standard deviations above, and I don't want to be more than 1.5 standard deviations below. So what does that mean in terms of z? It means that negative 1.5 is less than z is less than 1.5. Okay, so what is that? That's going to be equal to normal standard distribution, 1.5 on the one end minus normal standard distribution, negative 1.5 on the other end. Enter too few arguments. Because I needed to say it was cumulative. Right, 1, okay, and 1. Okay, so there it is. 8.866386. Okay, so that kind of completes our thought on that specific example there. Okay. Going back here. Let X have a normal distribution with mean mu and standard deviation sigma. Okay, if mu is 30 and sigma is 5, what is the 6th percentile of the distribution? So if mu is 30 and sigma is 5, what is the 6th percentile of the distribution? Okay, so again, we have a mean of 30, we have a standard deviation of 5, and I want the 6th percentile. Okay, and then let me just kind of get this other one down. The width of a line on a circuit chip is normally distributed with mean 3 micrometers. It's kind of unfortunate that micrometers has a mu actually appended to the front of it. 3 micrometers and standard deviation 0.140 micrometers. Okay, what width value separates the widest 10% from all such lines of all such lines from the other 90%? Okay, well, okay, so in this particular problem, we have a mean of 3 and we have a standard deviation of 0.140. And what are we being asked for? Okay, so this is our random variable is dealing with the width of things in this problem. Okay, and I want to kind of figure out what is the width at which I'm starting to encounter the top 10% of the data, the top 10% of the data. Okay, so that's, if I'm starting to encounter the top 10% of the data, that means 90% is below. So really that's asking for the 90th percentile. Okay, the 90th percentile. So the first problem is asking for the 6th percentile of a specific normal distribution. And the second problem is asking for the 90th percentile of a specific normal distribution. Okay, so let's go over into Excel and we'll deal with that. Okay, so how do I do it? So the first problem, I had an X that was distributed as normal with mean 30 and standard deviation 5. Okay, and I wanted the 6th percentile. I wanted the 6th percentile. That means I want a number at which I have 6% of the data below it. Okay, now you know that 50% of the data is below the mean for the normal distribution. So you would expect that this value, the percentile value, would actually be quite a bit below 30. Okay, so let's see here. Equals, so what do I want? I want a number. So let me just write this, okay? I want the 6th percentile. So the 6th percentile. What is it? The 6th percentile for this particular thing. So that means I'm going to go equals normal, normal inverse. Okay, I can do the inverse distribution of this thing. Okay, that means that it's going to give me the number that corresponds to a particular percentage. Okay, so what's the probability I want below this? Well, 0.06. What's the mean? 30. What's the standard deviation? 5. Yep, I'm almost done. Yeah, almost. Okay. And then what about the other case? So this means that basically the number 22.22613, 6% of the data sits below that. So this 22.22613 thing, that is the number at which 6% is below. Okay, in the other case, I had X distributed as normal with mean 3 and standard deviation 0.14. Okay, and we wanted the 90th percentile. How do I get it? Well, I go equals normal inverse. And by the way, we could have converted all of these things to standard normal and done a similar thing. Okay, by subtracting the mean and divided by the standard deviation and just using the standard normal. So what percentage do I want below this? Well, I want 90%. What's the mean? 3. What's the standard deviation? 0.14. There it is. Okay. And it makes sense that that is actually bigger than the mean. So 3 would have been the 50th percentile, the median, right? The mean and the median are the same for the normal distribution. So I would actually have to get bigger than the mean to encounter 90% of the data, to have 90% of the data below that. All right. So let's go back into here. Okay. So the automatic opening device of a military cargo parachute has been designed to open when the parachute is 200 meters above the ground. Suppose opening altitude actually has a normal distribution with mean value 200 and standard deviation 30. Okay. Equipment damage will occur if the parachute opens at an altitude of less than 100 meters. Okay. An altitude of less than 100 meters. Okay. So what is the probability that there is equipment damage in at least one of 5 independently dropped parachutes? Okay, so 1 of 5 independently dropped parachutes. Okay, so that's interesting. Okay, so let's go over here into Excel and let's kind of think our way through this one. Okay, so first of all, in this particular problem, we have X. This thing is distributed as normal. The mean altitude was 200. The standard deviation was 30. Okay. And what was the deal? I wanted to know, first of all, it would be nice to know what's the probability that there will be damage, right? If X is the altitude at which the thing opens and it has this normal distribution, damage occurs, right? So this is equal to probability of damage. Probability of damage. Probability of damage. Okay. Okay. So what is that? That's going to be equal to normal distribution. Okay. 200. Sorry, not 200. 100 is the X. The mean is 200. The standard deviation is 30. Do I want cumulative? Yes, I do. And I get that. But they said, okay, over in the presentation, they actually said, what is the probability that there is equipment damage in at least 1 of 5 independently dropped parachutes? At least 1 of 5 independently dropped parachutes. Okay, so 1 of 5 independently dropped parachutes. So that tells me that we want Y. Okay, so like the probability that Y is greater than or equal to 5. Now we really do care about equals. Where Y is distributed as, okay, so we have 5 independent trials. The proportion, sorry, it was 1 of 5, right? Y is greater than or equal to 1. And what is the distribution of Y? Well, it's going to be binomial with n equal to 5 And what is the probability of damage? Okay, well it's 0.000429. Right, so P equal to 0.000429. Okay. Okay, so because damage is going to occur in at least one of those, so damage here corresponds to success. Okay, that's kind of a weird way to think about it. In at least one of 5 independently dropped things, the probability of damage is given by that 0.000429 thing. Okay. So what is this thing? So that's going to be equal to 1 minus the probability of, right, it's just going to be P of 0 for this thing, yes? So that's equal to 1 minus binomial distribution. It's the binomial distribution. What's the number of successes? I want 0 successes. What's the number of trials? 5. What is the probability of success? It's this right here. Cumulative, no, I really don't need cumulative here. I just want the probability of 0, basically. Okay, what's wrong with this thing? So probability of success, trials, number of successes, cumulative, false. I just want false. What is wrong with this thing? Maybe it doesn't like the fact that I've put this thing in there. Maybe I'll just go 0.000429. Sorry, guys. Number of successes. Well, I'm not sure. Maybe it doesn't like it that I'm asking for 0 of the. Oh, I see. It doesn't like it that I've put 1 minus P of 0 in here. Sorry. Okay. And now I actually can put this thing in here. There it is. 0.002143. And by the way, I would have gotten the same thing if I would have gotten if I would have just said, well, the probability of zero of these things. So the probability of damage is just this, right? So I would have to go all right, sorry everyone, I was getting interrupted there. Okay, so another way we could have done this computation is by saying, okay, the probability that one of these, at least one of these chutes is damaged is equal to 1 minus the probability that none of them are damaged. And the probability of damage is 0.000429. So what you would have to do is you would have to go 1 minus this thing, right? So that's the probability of no damage. And we would have to raise this thing to the 5th power because we have to multiply all those things together. So this should give us the same number. And it does. So that's great. Great. Okay. So let's go back to our presentation. Okay. That's that. One thing that is important, and we've kind of alluded to this, especially with the chi-squared distribution, are these things called critical values. And a critical value, which we denote by Z alpha, okay, Z sub alpha, is simply, here, let me expand this so you can see it a little bit better, full screen mode. Okay, Z alpha is just a number on the x-axis within the standard normal distribution. Okay, remember we can put all normal distributions on this equal playing field with the standard normal. So it's a number Z alpha such that there's alpha percent of the data beyond Z alpha. So that means that the probability in that tail above Z alpha is just equal to alpha. It ought to remind you of kind of like the opposite of a percentile. So Z alpha, actually negative Z alpha would be the alphth percentile. Okay, so negative Z sub alpha. Okay, listen to what I'm saying. Negative Z alpha would be the alphth percentile rank for the standard normal distribution. Okay, so probability of things being in the tails like this is very, very important. Okay, so let's look at an example of this. Okay, so what about Z sub 0.07? Okay, Z sub 0.07 and Z sub 0.82. Okay, let's kind of look at that together. And we can actually do that in Excel as well. Okay, so let's go over to Excel once again. Okay, so I want Z sub, okay, Z sub 0.07. Okay, that's what I want. So that means that the probability that Z is greater than or equal to, in fact, it doesn't really matter that it's greater than or equal to, Z sub 0.07, that's going to be equal to 0.07, okay? So I want a number that has that property. By the way, that means also just by symmetry of the normal bell-shaped curve, the probability that Z is less than the negative of this number, Z sub 0.07, okay, that this is also equal to 0.07. And that's important because then I can actually use the cumulative distribution function to help me with that. In fact, I can go equals normal standard inverse of what probability do I want? Well, 0.07, okay? And I get negative 1.47579. So what that means, right, that's the negative of this thing, right? The 7th percentile rank is given by this, okay? So this thing right here is the 7th percentile rank. Okay, that's what this thing is right here. So what is Z sub 0 or 0.07? Well, it's equal to the positive of that, 1.475579. Okay, that's what that thing equals to. Okay, and what about Z sub? The other one we wanted was Z sub 0.82. Z sub 0.82. Okay. Well, that means the probability that Z is greater than Z sub 0.82, 0.2 is, which by the way, just by symmetry is the same thing as the probability that Z is less than negative Z, little z sub 0.82, equals what? 0.82. Okay, this is sort of strange, but yeah, we'll see. We'll kind of you'll see why it's a little strange. So we want the 82nd percentile rank. Okay, so we want the 82nd percentile is essentially what we want. That's what the second thing is doing right here. That's what this is doing right here. Okay, so what is it? Okay, what is it? Well, let's see. It's going to be equal to normal standard inverse. Okay, and we put 0.82 in there. Okay, and we get 0.91, right? So 0.915365. Okay, but remember that's what the negative of this thing would be. Okay? This thing would be equal to, okay, this guy right here is the negative Z sub 0.82. Okay, that's the negative Z sub 0.82. I shouldn't have put equals on there. Oh, that's the negative of this thing. Okay, the negative of that thing. It doesn't like that I'm putting those things in there. Okay, so that's what's going on with this thing. Okay. Okay. So what is this guy? Z sub 0.82 is equal to 0.915365. Okay. And why does that make sense? Or actually, it's the negative of that. Sorry. It's the negative of that. Why does it make sense that that thing would be negative? Well, I want a number such that the probability that Z is beyond it is 82%. Well, that right, the probability that Z is bigger than 0 is 50%. So I would actually have to have a negative number to increase that probability from 50% to 82%. Okay, so I would have to go below 0 to get that to happen. Okay. Here's a little, I'll actually go over here and show you a little picture of what's going on here. Okay, so here we go. Let's go in here. So watch this. The picture of what's happening here is this. Okay, so Z sub 0.82. Okay, remember 0 is right in the middle. Right, Z is the standard normal distribution. Okay, Z sub 0.82, well, you know that that's going to be down here somewhere. Because the deal is all of this area is going to be 82%. Yeah, and you know that this stuff from here onward, that's, right, from 0 onward, that's 50%, right? So that thing has got to be negative, okay? So the probability that capital Z is bigger than Z sub 0.82, well, that's the same thing as the probability that Z is less than negative Z sub 0.82. Okay. And negative of that's like up here. So that's kind of interesting, right? So instead of computing this guy, right, this guy all the way up, what we do is we go this guy all the way down. Okay, so this thing right here is Z's negative Z sub 0.82. Okay, that's what that thing is right there, negative Z sub 0.82. Okay. And we just discovered that this thing is, right, this thing has to be equal to 0.82. And what we discovered was over here, okay, we discovered this, okay, that the negative of Z sub 0.82 was equal to 0.915. And so the original thing is negative 0.915365. Okay. So that picture hopefully kind of clears that up a little bit. All right. Almost done. Okay. This is the very last thing I wanted to say. Okay. So if X is distributed as normal with mean mu and actually a variance sigma squared, you know, sometimes that notation varies from textbook to textbook. Sometimes you'll put the variance in there. Sometimes you'll put the standard deviation. Then the standard normal random variable squared, okay? If I take the standard normal and square it, which is just X minus mu squared over sigma squared, it turns out that has this thing called the chi-squared distribution, which is what we talked about with 1 degree of freedom. With 1 degree of freedom. Okay, so squaring a standard normal random variable gives you the chi-squared distribution with 1 degree of freedom. And where in the world would that come up? Well, you know that Z squared comes up when you compute very basic things like the variance. Okay, the variance for a random variable. You know, you want to compute the expectation of Z squared, for instance. So Z squared, the standard normal random variable squared, has the chi-square distribution. And that's, has the chi-square distribution with 1 degree of freedom. That will actually be important later on when we start doing something called confidence intervals. All right? All right. That is all we have from that material. We are going to move on to more with the normal distribution, and actually we'll look at some joint distributions, and eventually we'll talk a little bit about confidence intervals, and that's going to arise from something called the central limit theorem that is indeed very important for us. That's all for now.